The purpose of this video is to show you the mathematics behind simple harmonic motion, primarily for time period and for displacement of a mass spring system. So simple harmonic motion is displayed when the applied force to an object is equal but opposite to its restorative force. You can think about this in the pendulum lab because the applied force was when it was going in the forward direction, and the restorative force is when it was coming back to that original position. So what are some objects that actually exhibit this simple harmonic motion? Anything that acts like a pendulum, anything that acts like a spring, and then therefore anything that oscillates, anything that has a constant pattern over a period of time. So let's talk about how to define time period and frequency. We talked about this in the pendulum lab. Here it is in definition form. Period of simple harmonic motion is defined as the time it takes an object experiencing SHM to move through one complete cycle. Frequency is going to be the inverse relationship of the period. So frequency of simple harmonic motion, we'll change that to SHM, not SHS, is how many cycles an object can experience in 1 second. So these are inverse relationships of each other, which will be seen in these formulas. These are incredibly important formulas to have written down in your notebook. I'd pause the video and make that happen. So time period, capital P, is defined as 1 divided by the frequency. And 1 divided by the frequency, the units there is a second. And the frequency is going to be 1 over the time period. And when we use this frequency equation, 1 divided by the time period in seconds is 1 over seconds, which is also defined as the hertz. You've probably seen on your radio dial, at least what used to be there before current technology, when you have a radio station at a particular number, those numbers are the number of megahertz of that radio wave that is bringing that information from that radio station to your transceiver. So if I know the frequency, I can find the period. If I know the period, I can find the frequency because they're inverse relationships of each other. Knowing that, let's look at our first SHM system, that of a mass spring system. And before we go to this definition, let's look at the simulation. So when we're talking about a mass spring system, we're talking about a spring, and we hang some amount of mass to it, and that particular spring system oscillates. And so the applied force will be equal and opposite to the returning force. And I can really see this if I take away air resistance. So if I pull this down again, watch what happens. This could keep on going infinitely because I took away air resistance of that mass. Because if air resistance was present, this would not keep on going. And I can slow this down and see that the mass is going to return and go back to the same distance above the starting point each particular time. This is why a mass spring system is experiencing simple harmonic motion. So, a couple relationships with the simple harmonic motion in terms of a spring mass system. We can apply Hooke's law to a spring mass system, where the relationship between the amount of downward force applied to a spring when I pulled the mass down in the simulation and the spring stretch can be described with this formula, where F is going to be the up or downward force being applied to the spring. One is in the positive direction, one is in the negative direction, is equal to the spring constant, which you have learned about when we were doing about the energy unit a couple of months ago. And X is going to be the spring's stretch or the spring's compression. So after you have unpaused the video and copied down this formula, I'm going to again show you this mass spring system and how this applies to Hooke's law. Here are these masses again. I'm going to slow down this simulation to 1/16 of the real time, and I'm going to start by adding a 50-gram mass to the system, and I am going to put this ruler at the base of where the spring ended before I put the mass. So if I change my air resistance back to none and I pull down on the spring, that's the compression and that's the stretch. There's your compression again. There's your stretch, and if I go to the maximum value, notice it's stretched to about, well, we'll say 29 centimeters below the equilibrium position. If I increase that mass by 50 grams, you will see that when I pull it down and unpause it, the amount of compression and the amount of stretch will increase dramatically as well. And so this one happened to go down, and you can't see it, but about 49 centimeters as opposed to the 29 the last one did. This is a linear relationship. So if I added another 50 grams onto this mass, it would probably go up another 20 centimeters for a total of 69 centimeters of stretch and compression. So I can see this relationship graphically. This is a picture of a Hooke's law apparatus, which is similar to what you just saw in the simulation. But as I increase the weight or the force of gravity or the mass that I added to the end of the spring set, notice that the extension or stretch and compression went up proportionally, up until the point that I've reached maximum extension, because every spring has a point where it can't stretch anymore. So, moral of the story with Hooke's law, it's a linear relationship between the stretch of the spring versus the mass hanging at the bottom of the spring. Let's do an example problem that deals with Hooke's law. So the example question up here says a certain spring with a spring constant of 150 newtons per meter is loaded with an unknown mass on it. What is the value of the unknown mass if it causes the spring to extend 24 centimeters? So we want to know the mass of this particular spring. So here's Hooke's law. You're going to see here why we have a negative value in front of that spring constant. So looking at my example problem, I see my spring constant here is 150 newtons per meter, so I'm going to call that K. And I've got a spring to extend 24 centimeters, so that's the change in stretch of the spring. I do have to change that to meters, so that's going to be 1, 2 decimal places over, or 0.24 meters equals X. I also need to remember that force equals mass times gravity in this case, because the mass is hanging and stretching straight down. And so I can substitute this equation in for F. I can then, isolate mass by dividing both sides by gravity. And I have this new equation that the mass of the weight is going to be negative kx divided by g. So I'm going to have negative 150 Newton meters, 0.24 for my compression stretch of my spring. And here is why the equation is negative, is because gravity is negative, negative 9.8. And so when I solve all of this, multiplying the 150 times the 0.24, all divided by the 9.8, negatives cancel out, my mass is going to be 3.7 kilograms. Going back to the world of sig figs, 2 sig figs in my x value, 2 sig figs in my k value, so I have 2 sig figs in my answer. This is pretty much how simple it is to use Hooke's law to figure out the mass hanging from a mass spring system. How about the time period, though? So with this time period, you're going to have to do a little bit of mathematical faith believing, because there's some calculus involved in deriving this formula. And we're not going to derive this formula together, because a lot of you haven't done this level of calculus yet. So if I want to find out how long it takes a spring mass system to complete one oscillation, or find the time period, what I will do is use this equation, where the time period equals 2 pi times the square root of the mass divided by the spring constant. Again, know that there's some calculus missing here, and you may wonder how mass divided by newtons divided by meters is going to equal seconds. Take a leap of faith that it does. If you want to know the calculus why, I will show you. But for the time being, even though the units don't really reconcile themselves here, take it on a leap of faith that this equation will allow you to find the time period for any mass spring system. Where the 2 pi comes from, so basically there are 360 degrees in a circle. Or if I was to travel around the circumference of a circle, the amount of distance that I would cover is proportional to 2 pi. So all you need to know about radians in this case is that the 2 pi comes from the fact there's 360 degrees in a circle, and circles have no beginning or no end, and they're great representations of things that oscillate because they go up, down, just like a sine or cosine wave. So that's where the 2 pi comes from. Let's go back to this example problem and use that equation in order to come up with the time period of this spring mass system. So, we've got the time period equals 2 pi times the square root of the mass of the weight divided by the spring constant. It is just that simple. My units here for mass are in kilograms, and that's what you want it to be. My spring constant is still 150 newtons per meter. And then, if I divide these things out, and square root, try that one more time. And multiply it by 2 times pi. I find out that my time period, or the amount of time for one oscillation, is going to be 0.99 seconds. So that's how long it'll take for the mass to go up and compress, back through equilibrium, and stretch. What I mean by that is one of these oscillations, a stretch, back through equilibrium, and a compression. Stretch, equilibrium, compression. That is one oscillation or one period of that spring system. So I'm going to pause the video here because the next thing we're going to talk about is the pendulum, and we're going to do a little bit of algebra to derive that equation. But this is a great place to try the problems on the Schoology page, which will be on the Schoology page, page 381, 1 through 5. Page 381, 1 through 5. Thank you and have a wonderful evening.